Hi, my name is Matthew Gomez. For the past 6 weeks, I've been working on the design and integration of soft twisting pneumatic actuators for robots under the guidance of President Fairchild and Dr. Tan. So what are soft robots? So soft robots are robots that are able to interact with people and delicate items far better due to their flexible nature. They're usually made out of soft materials like rubbers and silicons, and that makes them much better in like unstructured environments such as disaster zones as well as agricultural applications. So in our case, that might be like an apple orchard or an asparagus field. So the purpose of our study was to optimize an existing soft pneumatic twisting design for a larger scale robotic system, as well as improving the fabrication techniques used to create geometrically complex soft robotics components. So what is like a soft pneumatic twisting actuator? So they're able to generate rotational motion through the use of positive and negative pressure. They have important uses within manipulating and grasping applications. So in our case, we would be using this to rotate an apple to reduce the total amount of force needed to remove it. So instead of just pulling on it, we're able to rotate it and reduce the total amount of force required to do that action. So our initial design consisted of a triangle and a bellow shape. So these two shapes were combined with each other and offset by a certain angle in order to generate the desired twisting motion. So there were four parameters that we found contributed to the changes in rotational motion, which were the radius of the circle on the bellow, the total length of the actuator, the angular offset between the top and the bottom of the actuator, and the width of the bellow from the center of the circle. So all of these factors contributed to how much rotation we were able to get out of the actuator. So in order to test our actuator, we used finite element analysis in Abacus in order to simulate the actuator's response to a variety of pressures. Additionally, we also used FEA to evaluate our material choices. So we started with a wide variety of materials that are used within soft robotics, and eventually we landed on Dragon Skin 20 silicon for its good elasticity as well as its high strength. So we're able to apply a lot of pressure until the actuator eventually fails. So this was the optimized design that we were able to generate. So this design almost gets 40 degrees of rotational motion. As you can see, so we get 40 degrees of rotational motion from like negative 4.4 psi up to around 6.25 psi. And those are some of the design parameters. Those are the design parameters that we used to generate this design. So these are the simulation results that we generated for a wide variety of designs. I just wanted to show this just because there's a pretty clear difference between the different designs. So the one that we ended up picking is the blue one that is almost at 20 degrees. This is just for positive pressure, no negative pressure here. But I wanted to mention two designs that you can see earlier. That with less pressure, they generate far more rotational motion than other designs. I just want to mention this just because there are probably better optimized designs that could take advantage of better rotation at low pressure than the design that we ended up using. So there's probably more room for improvement that we just haven't been able to find. So this is what the actuator looks like when it's actually being simulated. So red areas represent areas of high stress. Most of the stress is centered around the edges of the triangle on the top. And it hasn't failed yet, but that's where it does fail at those points. And it's a similar story when we apply negative pressure. So this is with negative 30 kilopascal pressure. It's the same areas on the top and around the edges. So for fabricating the actuator, we begin by creating a negative of the shape and using a resin printer to create the mold. So the mold looks something like this. We ended up using a resin printer just because of it's first super accurate, so we don't get like the weird bits of texture that you would get with a normal 3D printer. And also the resin has a much higher melting temp, which was very useful when we're melting out the wax. So right here, this is this sacrificial wax piece that goes on the inside of the mold. So this is a 3D printed wax piece. It melts at around 150 C. It's lower melting temp than the resin. The resin has a much higher melting temperature, so we're able to heat up both at the same time and just only melt this part of it. And we use 3 carbon fiber rods that go through it in order to suspend it in the middle of the mold and keep a constant wall thickness of 3 mil throughout the entire actuator. So this is the toaster oven that we use in order to heat up the wax. So that's a toaster oven in a fume hood. It does smell a little bit, so that's why we have it in the fume hood. So we kept it in there for a couple of hours to let all of the wax melt out, and eventually you are left with a slightly discolored, ugly-looking actuator. So as you can see, most of it has been most of the wax has already melted out. There's a little bit left at the top, but this is an early picture. I ended up melting that out too. And so after we put it inside of the toaster, we just have to trim like the edges. Some parts of it are a little charred, so we can remove those parts and add more silicon. And also at this point, we'd also add a tube that goes in the bottom of it, where we will be applying the pressure to it. So this right here is the experimental setup that we'll be using in order to test it. So this is a motion tracking system. It has 8 motion tracking cameras all around it. That is not the robot. That is not the actuator that we're testing. That's another one. But it's the same idea. So we'll be placing 3 motion tracking dots on top of the actuator in order to see how much it rotates. Just like some simple MATLAB script in order to calculate the rotation from the movement of those 3 points in space. So some of our next steps for this design, first would be fine-tuning the fabrication process of this. So the 3D printing part of 3D printing the wax mold is a relatively relatively novel or new idea within soft robotics. So there's a couple of issues that need to be worked out with it. The first issue with it is the wax seems to get warped sometimes, and what happens when it gets warped is, since it's 3D printed, it starts peeling and creates layers. So sometimes the silicon wants to flow inside of it, and it gets mixed in with the wax, making it very hard to get out. So obviously, like improving the 3D printing techniques that we use for wax would be to make a stronger piece. That would be really important. Additionally, we would like to integrate this with other robots. So you can see that robot right there. We'd like to give it the gripper a twist, the ability to twist to make it easier to remove apples. So yeah, that's that. And finally, we'd also like to test this in real-world environments. So to see how this would react, with sun and moisture and other external factors like a tree branch poking into it or something like that. It's important to know how it would react to those other things. So yeah. I'd like to say thank you to Dr. Richmond, obviously, for providing this opportunity, as well as everyone else here who's been here for the last 6 weeks with me. And obviously, I'd like to say thank you to Preston